here is lesson 106. In this lesson, we will continue to look at vector equation of lines, but instead of in 2 space, now we're going to look at lines in 3D space. So recall that a line can be defined by a point on it and also the direction vector for the line. And so to write a vector equation of a line in 3D space, you can see that we have just added the z component, right, into the vector equation of a line in 2 space. So you see the additional of z equals to a3 plus lambda d3 in parametric form. And then in Cartesian form, you have the additional last relation of z minus a3 over d3. And remember, to go from parametric form into Cartesian form, you are eliminating lambda, okay, the scale factor for the direction vector. Example 1. Given the Cartesian equation of a line x minus 3 equals to negative y equal to z plus 4, we want to determine the vector equation. So the first thing is we can turn this back into parametric form. I can put back lambda equals to x minus 3 equals to negative y equals to z plus 4. So imagine you're working with a pair of these equations at a time. Let's say lambda equals x minus 3. Isolate x, I have lambda plus 3. And then looking at lambda equals to negative y, y is equal to negative lambda. Lambda equals z plus 4 implies that z must equal to lambda minus 4. So this is in parametric form. Turning this into vector equation, the points are, well, this is plus 0 in the y parameter, so 3, 0, negative 4 would be a position vector of a point on the line, plus lambda times the direction vector of 1, negative 1, 1, where lambda belongs to the set of real numbers. Okay. Example 2. Find the angle between the two lines here. So when we are dealing with angles between the lines, we're referring to the direction vectors. So I have direction vector d1, 3, 4, negative 2, direction vector d2, 2, 3, 1. And then to find the angles between the two direction vectors, recall from the scalar product lesson, cosine theta is equal to the dot product, d2 of the two direction vectors over the product of their magnitudes. All right. Okay, so d1 dot d2, 3 times 2, 6, 4 times 3, 12, negative 2 times 1, minus 2. And then I need the respective magnitude, so 3 squared plus 4 squared plus 2 squared, square root. And then the other one is 2 squared, 3 squared, 1 squared. So I have this relation. Let's simplify. I have 16 at the top. Over denominator, I have 29 square root times the square root of 14. And of course, to find theta, I need to take arc cos of 16 over 29 times 14. And if I use my calculator to find this angle, it is 37.4 degrees, rounded to 3 significant figures. Of course, when we study lines in 3D space, one thing of interest would be how these lines can intersect each other. So if you think about intersection of lines on the Cartesian plane on the xy plane, we learned that the lines can coincide with each other, the lines can be parallel so they do not intersect, or the lines can cross each other at one point of intersection. It's very similar when we think about lines in 3D space with one additional possibility. So you see that the green pair of lines here, they kind of like follow different paths. So obviously they're not parallel to each other. However, they keep passing each other without crossing because like one line is kind of elevated. Even if it travels at an angle, it's going to miss the other line. You can think of maybe two airplanes in air, right? They could be flying at different altitudes, always at different altitudes. And so they do not cross each other, even if, that flat path looks like they will form a cross if you look from the top, okay? So these lines are called skew lines. So some terminologies here. We say that a linear system is said to be consistent if it has at least one solution. Otherwise, we say that the system is inconsistent. Example 3. We want to show that the two lines here are not concurrent. So here's another term, concurrent or not concurrent, let's do it this way, means that they do not intersect. Okay, in other words, concurrent lines do intersect. All right. So looking at line 1, which is given to us in Cartesian form, and because line 2 in vector form has a scalar of lambda, I'm going to use a different letter, say mu, to represent the scalar multiple of the direction vector of line 1, because I think it's easier if I can write this in parametric form. So x is equal to 3 mu plus 2. Y is equal to negative 2 mu minus 5. And then z plus 4 over 1. So I have z equals to positive mu minus 4. And let me make this bigger. Okay, so here is line 1. And here is line 2. So for two lines to be not concurrent, the first thing I will definitely check is the direction vectors of the two lines. So if I look at the first line, direction vector is 3, negative 2, and 1. And then the second direction vector is 3, negative 2, and 1. So first of all, I can notice that the two directional vectors are equal to each other. Then one thing for sure is that line 1 is parallel to line 2. Oh, I should use uppercase. Sorry. And because we have a set of parallel lines, for sure they will not intersect. Hence, not concurrent. So you see that by comparing the direction vectors, it's very convenient to tell whether two lines are concurrent or not. If you forgot about this trick, you can try to solve the system of equation, obviously, and see if there is a contradiction or whether you can find a point of intersection. So I'm going to get you started here. So I'm going to write down, alternatively, we can assume the lines do intersect. Okay. In that case, I can say that the x component should equal to each other. Y components will equal each other. And also, also the z component. Okay, this will give me a system of three equations with two unknowns. So 3 mu minus 3 lambda is 2. I have negative 2 mu plus 2 lambda, or 2 mu minus 2 lambda is negative 8. and then mu minus lambda, negative 1 plus 4, 3. Okay, and then maybe solve 1, 2 by elimination. I can do, no, 1, 2 is bad, 2, 3. Okay, so I can multiply 3 by 2. Okay, and then subtract the two lines. I got 0 lambda equals to negative 14, which, of course, is a contradiction. Because 0 times any number cannot be anything other than 0, okay? Because we have this contradiction, we can stop and say, therefore, the two lines are not concurrent. Okay. Look at example 4. Find any intersection between the following lines. So we have two lines in parametric form. That's convenient. Let's compare their direction vectors. So D1, looking at the coefficients of t, I have 1, negative 1, and 1. D2, looking at the coefficients of s, I have 2, 3, and negative 1. So obviously I cannot write D1 as a scalar multiple of D2. So there are two possibilities. The lines are either skew, right? They can't overlap, they can be parallel, or have one point of intersection. Okay, so we have to try and solve them, the system of equations, to see which case it is. So assuming they do intersect, we can say that 2 plus t, dx, is equal to 3 plus 2s. 1 minus t is equal to 3s. And t is equal to negative 1 minus s. This, we can rearrange the terms. We have 2s minus t equals to 2 minus 3, negative 1. That's equation 1. 3s plus t is equal to positive 1, equation 2. And I can say I have s plus t equals to negative 1, equation 3. Let's try to solve, maybe using equations 1 and 2 by elimination. If I add the two equations together, I have 2s plus 3s, 5s. Negative t plus t, 0, equals to negative 1 plus 1, 0. So s would equal to 0. If I sub s equals to 0 into, let's say, equation 1, I have negative t equals negative 1, or t equals to 1. Now, note that we have only used the first two equations in the system. We don't know what's going on in equation 3. So we're not done yet. We can't just assume that s equals to 0 and t equals to 1 works. What we have to do now is to, let me go higher actually. Okay, let's go here. We have to check whether s equals to 0 and t equals to 1 works in equation 3 or not. Okay, so the left side is s plus t, 0 plus 1, which is 1. The right side is negative 1. So since left side does not equal right side in equation 3, we cannot say there is a point of intersection, right? Because it doesn't work. We have an inconsistent system. Therefore, L1 and L2 are skew lines. They do not intersect, okay? Example B. This time we have two Cartesian equations for line 1 and line 2. Knowing that eventually we'll probably be solving these equations, it's a good idea to write it out in parametric form first. So L1, let's use the parameter s. I have x equal to 3s minus 1. Y is equal to 4s plus 1. And z is negative 2s. For L2, we're going to use t, okay, as the scalar multiple. So 2t minus 1 for x. Y is 3t. And z, we don't have a denominator, so it's over 1. That means it is t minus 7. Okay, let's compare D1 and D2. So direction vector of line 1 is 3, 4, negative 2, the coefficients of s. D2 is 2, 3, 1. I don't think I can write these as scalar multiples of each other. Once again, L1 and L2 have one POI or are skew lines. Okay? So once again, assuming they intersect. Okay, assuming that they intersect, now we can compare the components. So 3s minus 1 is equal to 2t minus 1. 4s plus 1 is equal to 3t. Negative 2s is equal to t minus 7. This can be rearranged into 3s minus 2t. Negative 1 plus 1 is 0. 4s minus 3t equals negative 1. And negative 2s minus t. So why don't we do 2s plus t equals to positive 7. Okay? What's easy to use here? Well, equation 3 is definitely easy with the 1t there. So maybe we can use 1 and 3. Okay. If I do 3s minus 2t equals 0, which is equation 1, and I want to eliminate t, so 3 times 2 then. I have 4s plus 2t equals to 14. I will be adding the two together. 7s equals to 14, s is equal to 2. And then summing this into equation 3, I guess, t would be 7 minus 2 times 2, 7 minus 4, 3. All right. Now, because we use equations 1 and 3, you got to check s equals to 2, t equals to 3 in which equation? Equation 2, right. So left side of equation 2, 4 times 2 minus 3 times 3. This is 8 minus 9, negative 1, which is equal to the right side. This is good news because this is different from what we found. This means that the system is consistent. What does this mean? We have to do more work because now if we have a consistent system, we need to find the point of intersection. Do I use S? Do I use T? It doesn't matter because there should be the same point of intersection now. So I'm going to use 2. So sub S, oops. Okay, hey, what am I doing? Sub S equals to 2 into line 1. All right. So using parametric form, I have 3 times 2 minus 1, 6, 5. Y is 4 times 2, 8 plus 1, 9. Z is negative 2 times 2, negative 4. Therefore, the lines intersect at the point 5, 9, and negative 4. And that's it.